I'll continue with the discussion of the last lecture. We were talking of different types of architectures, and I talked about the concept of RISC and CISC style of processor design. This was a concept introduced by Peterson and Dietzel in 1980, and then their group, as well as one group at Stanford, they developed processor based on the proposed ideas. And in fact, in industry, all the new designs which have taken place have been based on the RISC idea. So the reference to the paper is this. It's a 1980 paper, and what it discusses is that what made computer designs complex, and from there emerged the idea of making them simpler. So it discusses what are the consequences of following CISC type of approach, that means working with complex designs, and how it makes more sense for RISC approach with VLSI technology that emerged around that time. So first, let's try to understand the history, why there was a trend to make processor more and more complex. So we need to understand the factors that motivated design of complex processors. Okay, why people wanted to design more complex processors, and also what facilitated this trend. Okay, what made it easy and possible. So just 1 minute. Got a message that somebody is waiting to join. I can't see that. Anyway, let me continue. So first, motivation for complex processor design. So the attempt was to provide some facility for carrying out common tasks which are typically required by high-level language programs. So many high-level languages would support, in high-level language you have abstractions which would need a long sequences of instructions. So if you provide complex instruction which can facilitate that task, the program would appear more compact. And at that time, memory was expensive, and slower than processor, about an order of magnitude slower. Then executing a sequence of instructions to do that task would consume not only more time, but you will have to access memory multiple times to get those instructions. So if you build that functionality in hardware, it would not only save the space you occupy in memory, but the memory accesses. Okay, so that was the philosophy why there was a trend to introduce complex instructions. And another reason was commercial. That is, a company wants to bring out a new machine, new design. You would like to retain everything which is there in the previous generation or previous version. Okay? So new generation, a new version comes up with something added to the previous one rather than a fresh design. So you don't want to lose compatibility with the previous one, and therefore it it's only additions that take place, and uh, from one generation to other generation, design would become more complex. So also there would be trend that, okay, if competitor has that instruction, my machine should also have that, and uh, so it keeps going that way. Now, uh, to understand what made it possible to design complex instruction, we need to understand the implementation approach. So at that time, processors were typically implemented using what is called microprogrammed control. And adding instruction was made easy by adding more microprogram code or microcode. Okay, so it's like a processor sitting within a smaller processor sitting within your controller, which actually interprets the instruction. So that microprogram code is stored in a small memory within the processor that's called control store. So for example, in one machine in a company PDP-11, its size was 256 by 56, which means 256 micro instructions, each of 56 bits. Okay, and its successor VAX11 780 had these many, 5,120 instructions, each 96 bits. Okay, so I'll come in a moment to explain what this control store is. But on the other hand, the simpler processors could be designed not by this approach, but just using a finite state machine to control. So, what is this control approach which is different? Uh, Typically, any digital system, just a minute, could be thought of in two parts. There is data path and there is controller. Okay, so the other side is controller. The data path is where you have adders, multipliers, registers, multiplexer, so where data flows, computations are done, results are stored, and so on. The other part is the controller, which steps through various operations with as the clock progresses. So as clock goes on, uh, the controller would change its states and produce control signals which will tell the data path what to do. And there could be signals going from data path to controller, which might make a choice in what is the next state. So the controller could follow a sequence of states, but at some point it may need to decide what is the next state, and that decision could depend upon maybe some comparison happens in the data path, and result of that decides what is the next state. So this is a typical approach where controller is simply a finite state machine. Uh, the output of that machine is the set of control signals which are required by the data path, and input is the result of some operations in a data path. These are called status signals, and that's how machine progresses. This may have some signal coming in and going out, uh, connected to the external world also. Okay, so this is a classical picture of a digital system, and that's how a simple system can be designed. But the approach in complex process design was like this, that here you not only you have a complex data path, you have a lot of control signals which are required, and these signals could be simply read out of a memory. Okay, a memory word, which is this memory sitting inside the controller, called microprogram memory or controls memory control store. Uh, you read out a word from this, and that word or a bit pattern drives the control signals. Okay, so rather than thinking of a finite state machine, you think of the sequence of control signals stored in memory. And this memory is addressed by, you can call, a microprogram counter, okay, which steps through this. And the next value of microprogram counter could be a simple, it could go in a simple sequence, or could make a decision based on status signals and some bits of the micro instruction itself. Okay, or you can put it this way, that some bits in a micro instruction would decide whether you go to the next instruction, next micro instruction, or based on the condition, you make a choice here. Okay, so one way or multi-way branch would happen. So it would look like a small processor sitting here. That's why it's called microprogram control. Now, uh, now you can visualize that if you need to add some functionality, you don't necessarily have to change the data path. Okay, within same basic element, basic operation which are present here, you could follow a certain sequence of operations to implement a functionality by and that means you add some more instruction to your microprogram here. Okay, so that's the background of how processors were desired to be complex, and it was possible to make them complex. Any question at this stage? Okay, but it turned out that although you may have some hundreds or thousands of instruction, only a few instructions were used by compiler. So for one to write a compiler which can make good use of all the huge number of instructions is not practical. So compilers would tend to just focus on a small subset, and therefore the rest would be waste and not add to the productivity. Uh, with the uh, if you uh, take care of the processor memory performance gap, then a sequence of simple instructions would become faster than a fewer complex instructions. All right. Firstly, because simple instructions could be implemented much more efficiently and faster as compared to complex instructions. So adding some complexity actually slows down clock or the number of cycles required for instructions uh, otherwise. Okay. So with better memory organization, better memory technology, the advantage of code density also diminished. And the benefits for high-level language features were questionable in the sense that you provide instruction for some specific uh, feature, but that may not be general enough to justify its presence. Okay, so providing something very specialized is also not always beneficial. And because of complexity, the design time is much more. So, for example, a simple design could be turned out in a few months or less than a year, whereas a complex design would take a couple of years. And by that time, the technology might change. And so you would design for today's technology, and by the time the product is out, the technology itself has uh, improved by a certain factor, and designs which even started later could actually uh, benefit from that technology. So by technology, what we mean is the technology of integrated circuits. And as the uh, technology grew, the packing density or the number of transistors you can put in a chip kept growing. Okay, so the scale changed from SSI, MSI, LSI to VLSI, small scale integration, medium scale integration, large scale integration, and very large scale integration. And the attempt was to uh, have entire processor fit in a chip. So simpler processor design made it possible to fit the whole thing in a chip. And as I just mentioned, short design time suitable for rapid changing technology, and it provides efficient implementation. So even if there is enough space on the chip area you would save by a simple design could be used for performance enhancing features like cache memory organization and pipelining, etc. Okay, so just to uh, summarize the discussion, uh, the proposed characteristics of reduced instruction set computer are that you have very limited number of formats. Instructions are of uniform size. Okay, as we will see example of CISC, we will find that the range of instruction size varies from very small number of bytes to large number of bytes. But in RISC processor, all instructions are of same size, typically one word. It began with 32, but there are 64-bit version, 16-bit versions also. A simple set of operation, all of primitive nature, and limited ways of addressing the memories. Addressing modes are just a few simple ones. In terms of location of operand, the instructions typically follow RR approach or register-based approach. Okay, so it's RR architecture, and because you're not providing memory addresses directly within the instruction, you have space for three addresses, two operands and one result. So this is a common feature that you have three address instruction for arithmetic logic operations. And memory addressing and computation are separated. So there are separate load instruction or store instruction. And in arithmetic instruction or logical instruction, you don't access memory for the operands. Okay, so if you have some computation to be done over data stored in memory, you need to bring these two registers, do computation, store the result back. Okay, complex processor tend to directly work with memory. That is, you take operand from memory within an instruction, perform operation, and store the result. Uh, now, um, I mentioned. Let me just get back to this point. So I said that area saved usable for cache and pipelining. In fact, pipelining of complex processor is very difficult because there are different instructions of different complexity. They take a different number of cycles for completion, and pipelining those is extremely difficult. So with a architecture of this kind, uh, you will find as we go further in the course that pipelining is fairly easy as compared to complex cases. Uh, so some of the early examples of RISC are MIPS processor at Stanford and Berkeley RISC at UC Berkeley. MIPS was commercially used by NEC, Nintendo, Silicon Graphics, Sony. So several companies used it. Now it's not so much in use. Sun Spark had been a prominent RISC architecture used by Sun and other companies like Texas Instruments, Toshiba, Fujitsu, Cypress, and so on. PowerPC was developed by a consortium of IBM, Motorola, and Apple. Okay, it was derived from an early architecture of IBM called Power, and it got used in some examples, as you can see. Hewlett Packard, another major computer company, uh, designed PA RISC. PA stands for Precision Architecture, RISC, as you know. DEC. Uh, DEC was the company which had PDP-11 and VAX-11. So they also brought out a RISC architecture, Alpha. And what we are studying now, ARM, was brought out a little later as compared to the other ones. It found application. It was also used by other companies mentioned here, and initially it came up as processor for embedded design, where processor you have a small processor part of an appliance or something. Okay. Interestingly, even one old machine, CDC 6600, which is of 1960s, had some of the features which were later on known as RISC. So this term didn't exist when CDC was there, but it actually had features which are typical of RISC. Now, on the other hand, example of CISC architecture, the mainframes were typically CISC. So CDC, which was also a mainframe, which I just mentioned, was an exception. And this VAX-11 780 is a classical example of something which is very complex. Okay. It was upward compatible with PDP-11, which was a mini computer. Then Motorola had this X stands for, X indicates a series of generation. So 68,000, 68,010, 68,020, 3040, and so on. So whole lot of machines formed a series. And this was used in Apple Macintosh and other desktop computers. Intel 80x86. Okay, so again, this stands for 80186, 286, 386, 486, and so on. And now we just call it, in short, x86 architecture. So this has been extensively used in personal computers as well as servers. So this was Intel's 16-bit processor or even 8-bit processor were designed well in time for IBM to choose those for PC. So, the personal computer, which was initially called IBM PC, was designed by IBM and they chose Intel's processor. So initially, Motorola and Intel were companies producing small chips for basically embedded applications. So Intel's initial few processors were called microprocessor, and they were used in embedded applications. But when the complexity grew, it became suitable for general purpose computing on PCs. Okay, let's look a little further into these architectures. And among these RISC architectures, we find a lot of similarity. So MIPS is a classical design of extreme simplicity. Only 3 very simple formats. Okay, we will see a little bit further. So just 3 types of instruction. There are no flags. Okay, there is comparison is done by an instruction called SLT, set if less than. I did mention an instruction of this kind in one of the earlier lectures. So it does comparison, and the result of comparison is put in a register. Okay, so there are no flags. That also takes away some complexity. And there is a peculiar instruction, load upper immediate. So there is, when you have instruction of uniform size, one word each, then loading a one word wide address into a register is a problem, because you can't specify that constant address within the instruction. So this processor provides instruction called LUI, load upper immediate. So you load a 16-bit number in upper half of a register. Okay, and then use another instruction to put the lower half. Okay? You can use add instruction or instruction, and that's how you get a 32-bit constant into a register. So two instructions. With each opcode, there is a implied addressing mode. So you don't. There is no separate mode addressing mode field in the instruction. So add and add immediate are two separate instructions here. PowerPC is the basic features are similar, but it does have condition registers, and it has predication like what we have seen in ARM. So predication means that you can put a condition with the instruction. So a large number of instructions can be predicated. In ARM, we have seen that every instruction has a condition field. So you can attach a condition with every instruction. In MIPS, there are no conditional instruction, only conditional branches are there, but this has quite a few conditional instructions. So there is a link register for subroutines and also for loops. So implementation of a loop also requires going back to the starting of the loop. So a link register which is there can be used for that purpose also. It remembers the starting address of the loop, and at the end of the loop you can use that address to go jump back. There is also a special counter register which is again used for loops. You can update the counter and perform a branch for controlling the iterations of the loop. So in MIPS, you can see that it is strictly a case of having just general purpose registers, nothing else. But here a few special purpose registers are added in PowerPC. Spark also has basic features which are similar. One interesting feature it brings out is that of register windows, and it also has condition flags. So I'll explain register windows in a few moments. Then we talk of advanced RISC machine or ARM. Interestingly, this is not available as a physical processor chip, not available as a physical device. It is available as a design. Okay, as a design core, which can be used by any other manufacturer to build a system. Okay, so people, for example, Samsung would take ARM design and build a system on chip around that. So you add add some circuitry, add some on-chip memory, add some peripheral interfaces, and then manufacture the chip. So ARM does not manufacture. ARM only sells the design of the processor. So the implementations are done by other companies, and a wide range of implementations have been done with different performance points, which means that some implementation may be faster but might consume more power. Other implementation may be somewhat slower but conserve power. So depending upon the application, same core can be used in variety of ways. And because it has entered the handheld device segment, billions of devices based on ARM have been shipped, and it's a dominant architecture across many market segments. So it is the architectural simplicity that has led to very small implementation, allowing devices with very low power consumption. Uh, there are variations in ARM design, ARM architecture itself. One is that it can work in a 16-bit mode, which is called thumb mode. So many processors uh, would normally be working in 32-bit mode, but they also support a 16-bit mode, which is called thumb mode. In that, the computation may be slower, but it saves power. Okay, so saves the instructions are represented in 16 bits. More or less similar instruction set is there, but with some restriction. For example, you may not have a 3 address structure. Okay, instead of saying add R1, R2, R3, you may say add R1, R2, which means that you perform addition of R1, R2 and put back result in R1. So one register uh, acts as one of the operands and the destination of the result, as we have seen in 2 address instructions. Then there are a couple of extensions of ARM. Of course, ARM itself has a series and family of architecture. So ARM 7, 8, 9, and so on. Various generations are there, but there are some extensions also. Yeah, was there a question?
So here, what do we mean by 16-bit instructions? Like, aren't we already having 16-bit instructions in the ARM?
No, the instruction set we have studied is 32-bit instruction.
Okay.
Okay, but almost similar instructions are available in 16-bit format also. So processors are designed to work in 2 modes. That is, you read one word of memory, which is 32-bit. That's one instruction. And then you read next word and so on. But when you switch to thumb mode, then you read half word, interpret that as instruction and execute. So two instructions, two thumb instructions can be packed in uh, one 32-bit word. Okay, uh, among extensions, there is an extension for efficiently executing Java bytecode. So these extensions are, so one may, let's say there is some company which is building a system with ARM architecture. Okay, so this is an optional addition that it may include this Jezel instruction or not, depending upon whether that application uh, considers interpretation of Java bytecode as important or not. Okay. Uh, so Java bytecode, as uh, you might know, is that Java programs are translated into an intermediate code called Java bytecode. So it's a sequence of bytes, each indicating some basic operation. So it's like a machine code, but code of an abstract machine. Neon extension is for SIMD operation, that is single instruction, multiple data. So same operation uh, you do over several pieces of data. For example, if you are adding two vectors, okay, so you want to add A1 plus B1, A2 plus B2, and so on. So you would take multiple operands. Uh, I shouldn't say multiple operand. So from, let's say, two vectors, you may take multiple elements and then add them together, or perform some such operation on multiple elements of the vector. VFP is for floating point. So floating point is not part of the basic ARM instruction set, but it's an add-on. Okay, let's look at now register structure of some of these processes we've been talking of. In MIPS, there is just one set of 32-bit registers, 32 registers of each 32 bits, and PC. So there are no other special purpose registers. PC is separate from these 32 registers. Uh, the memory is addressable by 32-bit addresses, 32-bit byte addresses. So 2 raised to power 32 bytes or 2 raised to power 30 words are possible. So MIPS has a small set of addressing modes, and you need to specify, you need to uh, look at the addressing mode when you are accessing operands. So how do you address memory? What is the mechanism? What arithmetic you perform to compute the address? Okay, so for operands and for destination of the result, and also jump target. So when you are branching or jumping to some instruction, you need address specification there also. What are the modes which are there in ARM? Sorry, MIPS. Immediate mode, that means address is part of the instruction. Register mode, that means instructions specify a register, and register contains the operand. Okay, the operand is contained in the register. Uh, the base and index mode means that there is a base part and then index part which you need to add and get the address. Okay, the base in MIPS, base is provided by a register and index is a constant. One could actually interpret it other way also. Then there is a PC relative addressing mode, which is typically used for branch instruction. Here, the target address is provided as a relative offset with reference to PC or the current instruction. And then there is direct addressing mode, which means the address is specified as part of the instruction. So compare it with immediate. In immediate, we are specifying a constant, which is the data. In direct mode, we specify a constant, which is the address, the jump target. Okay. I'm qualifying it by saying it is pseudo direct in the sense that since you can't specify entire 32-bit address in the instruction, in MIPS it is actually, if I remember correctly, it's just 26 bits field is there. So you can specify the address within a segment of the size 2 raised to power 26. Okay, so if you can think of memory as segmented into 2 raised to power 26 byte segments, then within the current segment you are specifying this address. So it is direct, but in a limited sense. Register indirect means that you specify register as part of the instruction, and that register contains the address. So indirection through a register, you are accessing memory indirectly through register. Okay, so as opposed to direct, where you are specifying address within the instruction, Register indirect means that you are specifying address in the register. So these are the three formats which I mentioned. Uh, okay, let me look at the last one first. So instruction like add, subtract, logical operation, and or and so on follow this format which is called R format, register format. Here there is a 6-bit opcode. There is a space for 3 registers, 1 destination and 2 sources. Uh, there is a 5-bit field which is not used. 5 bits are not used because we don't need. And this is another 6-bit field which is like an extension of opcode. Okay, so one group of instruction has one opcode, and within that group, instructions are differentiated by this field. So instruction like add, SLT, jump on register, they are all following R format. Uh, so this shift amount is used by shift instructions. So there are separate instructions to perform shift, unlike ARM where shift is part of um, the DP instruction. Here separate instructions are there for shifting, and those instructions use this field, otherwise this is not used. Uh, Now let me jump back to the first one, which is called I format. I stands for immediate format. So here you need 2 registers only, 2 register fields, one opcode field, and a 16-bit constant or immediate field. Okay, so you can see that 6 plus 4 plus 4. So since there are 32 registers, or register fields are 4-bit field. Okay, so 4 plus 4, 8, and 6. What am I missing? 6. I'm sorry, these are 5-bit field, not 4. 32-bit registers, a 5-bit field. So 6 plus 5 plus 5. So that is 16, and another 16-bit field. Total of 32. This is a constant or immediate field. For instruction like add immediate, you are specifying one of the operands here. Okay, and one of these two is a destination, other is a source. So one operand is a register, other is a constant. In instruction like load, so LW is load word. So you have a destination register, one base register, okay, and a 16-bit offset to the base. That becomes the memory address. And here is the J format for jump instruction, or so jump is like unconditional branch. Okay, conditional branches follow the I format, where in opcode itself you are specifying the condition. Uh, so in this JAL is like BL instruction of ARM. So jump and link. Here you are specifying opcode and just uh, direct address, but that address is within the segment. Okay, next we look at PowerPC architecture. I mentioned this already, that it was developed by a consortium and based on a previous architecture of IBM. There is a 32-bit version as well as 64-bit version. So in fact, for many architectures, including MIPS, 64-bit versions have come out. All right. ARM also has a 64-bit version, and x86 architectures also have 64-bit versions. So it has 32 general purpose registers. Apart from that, uh, there is a condition register which contain different flags. Okay? And those flags are set by arithmetic logical instruction and are tested by conditional branch instruction. The link register stores the return address for procedure calls and loops, and count register used for iteration count for a loop. Uh, Spark was right from the beginning designed for scalability. That means you have uh, you have scaling with respect to the word size. That means 32-bit architecture and a compatible 64-bit architecture, and also scaling in terms of uh, the performance by using better and better technology. One of the interesting features in Spark, which is quite unique, is the concept of register windows. So uh, a programmer sees basically a set of 32 registers, all right? But this set of 32 may be different in different contexts. So, for example, uh, you divide these 32 registers into 4 parts. First registers are first 8 are global. That means you will always see same registers, but the remaining 24 registers could change from time to time, and these form a part of a large register array, okay, which could be depending upon implementation 128 register, 256 register. So out of large array, uh, you have a window looking at only 24 registers. Okay. So at some point of time, let us say uh, you are looking at these registers. Um, these are divided into. Um, okay, I'll come to that in a moment. But first, let me mention that the window could change as you make a call to a function or return from a function. So at one time, you're looking at these 24 registers. You go through a call, uh, the window slides, and you are looking at a different set of registers. And when you come back, you may again look at the same registers. So these registers are divided into 4 groups, as I mentioned earlier. Global ones are same across the context. There is one set of registers which are called out, one set which is local, and one which is in. So 8 to 15 are out, 16 to 23 are local, 24 to 31 are in. So you can see that as you go from this window to the next window, what is out here becomes in. Okay, so it's like this space could be used for passing arguments to a function call. So whatever values you want to pass to the routine, you put those in this region. Okay. So what appears as register number 8 now, when you switch the window, it will appear as register number 24. Okay. So the input arguments could be picked up from these registers 24 to 31, and 16 to 23 are for local utilization, local work. And for next deeper call, you can put the operands in 8 to 15 and make a call, then the window will slide further down. So you could go to certain depth of calls, and this avoids the need for saving registers in the memory. Okay, so in ARM, we have been talking about saving register, restoring them, but that need is considerably reduced here. So as you can see that the callee would work on a different set of registers as compared to caller. The overlap is basically for passing the arguments, right? So in callee, you are not disturbing the values which caller had put in some of these registers. Okay, and that means you can safely work on a different set of registers. Of course, the overall size of the entire structure is limited. So after a certain depth of calls, you will reach the limit. And it is only at that stage you need to start saving in the memory. So suppose the size permits you a depth of 5. Okay, then you go one level deeper. Then you have to you have to save one set of registers in stack or some area of memory, and then later on restore. So when things become deeper, you need to start saving. Any question on this? So here is a comparison of the format of DP instructions for various RISC processors. So this first row is for alpha, next is for MIPS, PowerPC, PARISC, Spark, and ARM, which you are more familiar. What you would notice is that blue fields represent opcode. Okay, they are specifying the operation, and white ones are specifying operands, which are registered in these cases. Okay, so we are looking at instruction of the type add R1, R2, R3. How would they get specified in different processors? So let's look at MIPS, which I mentioned in detail. So there is a 6-bit opcode, 3 register fields, 5 bits not utilized, and 6 bit which are extension of the opcode. Okay. The superscripts here refer to the size of the field. Okay. All register fields are 5 bits, as you can see. There is a lot of commonality between some of these. Spark is a bit different, where opcode is spilled onto this field and this field. Okay. Uh, in ARM, the first field is the condition field. So I'm including that also as in a way specifying the opcode. For example, you have add EQ. So at assembly level, you are looking at it as a different instruction. So this by adding a condition, it actually make it a look like a different instruction. And this where shift specification is done, this also gives an impression of multiple instructions. Okay, so this tells you whether you have to shift left, shift right, by how much amount, and so on. So that is extending the instruction somewhere. And the real operands are these. These 3 4-bit fields are there: RD, RS, and RD. Okay, source and source 1, RS and RS1, RS1 and RS2. So this is the destination and 2 source fields. Just for uniformity of convention, uh, I put RS1 and RS2. Otherwise, we have been talking of RM and RN, same thing. Uh, the instruction with immediate field. Okay, either operations like add immediate or load store instruction where a constant offset is provided. So once again, you would see a lot of uniformity across some of these machines. Okay, opcode, 6-bit opcode, 2 register and 16-bit constant. Spark has a smaller constant because more bits are occupied in opcode. Uh, in ARM, we can look upon this as so actually this should have been 12, 15, 19. There are 8 bits here actually. Yeah, so it should have been put as OPX 8, not 3. 3 is not correct. So you would recall that in ARM, load instruction, for example, has a 6-bit opcode field plus 2 bits, which we have made as F field, F or the format field. So total of 8 and 4 for condition. So this all this together, 12 bits are specifying what operation it is. Okay. 2 registers are involved and a 12-bit constant. Conditional branch. So in ARM, this is the condition part, the opcode part 4 bits, and then remaining 24 bits are branch offset. Okay. Here you can see a lot of variation. Uh, some processor specifying 21 bit, 16 bit, 14 bit, 11, 19. So a lot of variation is there. Uh, Unconditional jump. So since it is unconditional, not even there are no condition fields. So you have larger space for the constants. Even in ARM, you have same field as same structure as conditional jump because there is no separate unconditional jump here. If you make condition field contain 14, that means it is branch always. Okay, that's unconditional. All right, let's look at example of some CISC architecture. So we'll look at example of VAX and x86. So as we've been saying that objective in these architectures have been to minimize the code size and make assembly programs look shorter and compact. But the instructions could vary in size from 1 byte to 54 bytes. Okay, so you can see the extreme. In the RISC machines, all instructions are uniformly 4 bytes. Okay, here they could be 1 byte to 54 byte. Uh, the words, the data is basically 32 bits, and so are the addresses. Um, so the addresses could be virtual. There is a basic support for virtual memory in the processor itself. Uh, 16 general purpose registers. So this is somewhat similar to ARM. R15 is PC and R14 is not linked register. Here it is. SP, and there are condition flags, condition codes. The interesting thing here is that the instructions are orthogonal in the sense that with every opcode you can specify every operand, every uh, addressing mode. Okay, so there are no exceptions. You can have all possible combinations of opcodes and addressing modes. And memory to memory instructions are supported. Recall the classification as RR, RM, MM, etc. So it supports MM, RR, all possibilities are there. Now, how do you interpret such an instruction? So how do you know that when you are going through sequence of instruction, how do you know where does the next instruction end? So you look at one byte, uh, that helps you in figuring out what the next bytes are and whether at all there are more bytes or not, or the instruction ends in first byte itself. So you need to first interpret that byte, then you know uh, what to make out of the remaining bytes. The opcode specifies which operation is to be done, how many operands are done. For example, is it addition of two numbers or three numbers? What types of operands are there? Uh, so on a variety of data types, the same operation may be valid. The data types could vary from 8-bit to 16-bit to 32, 64, 128. Okay, so when you say add, you'll have to specify whether you want to add 8-bit operand, 16-bit operand, 32-bit operand, and so on. You have data could be characters, each character being 1 byte, or it could be decimal digits. So decimal digits 0 to 9 encoded in 4 bits. So you could think of string of decimal digits. Variety of addressing modes. The immediate operands could be 6-bit, 8-bit, 16-bit, 32-bit. So 6 bits are called literals. Register mode, that means operand is in the register itself. Register deferred means that register has the address of memory. Uh, the displacements or the offset with respect to the base could be 8-bit, 16-bit, 32 bits. And so there could be indirection through memory. That means you specify a memory address, and at that memory location you have an ultimate address. All right. So if you are, for example, referring to, uh, suppose you want to have a array A, which is indexed by ith element of array B. Okay. So Bi is providing the address or the index for A. So you can imagine that you would need uh, to first get value of Bi and then use that to get value of A of Bi. So for that kind of scenario, there is you have index plus displacement, you get an address, and at that address you get the final address. Okay, so indexes could be scaled. That means base plus index, which is multiplied by some scale factor. Auto increment, auto decrement. That's like ARM we have. Okay, so auto increment, auto decrement means that you are incrementing or decrementing uh, the base register, and the computed address gets stored back into the register. That with further, possibly further indirection. So I'm putting deferred in square bracket means as an optional item. So some example of complex operations. You have data transfer where you can move one string from one place to other place. Okay, so essentially block of data can be moved by single instruction. Arithmetic logical operations could work on 2 operands as well as 3 operands. You have the usual control instruction, branch, jump, etc. The function call instruction, like we have BL, which simply transfers the control and saves the return address. But here function call would save the state. That means registers are also saved automatically when you make a function call. Of course, it will take several memory cycles because many registers have to be saved. But in program, you see just one single instruction. The instructions for bit manipulation, floating point operations, computation of cyclic redundancy check, insert in queue, and so on. So the huge set of instructions. So I'll show one or two examples. Uh, so this is one instruction where you're specifying various things. One is this: you're performing add. It is add immediate, 3 operands, and there are 3 parameters specified here. R1, 737 as the base with R2 as the index, and an immediate 456. Okay. So 3 operands are added, and the result is put in R1. Uh, so how is this instruction represented? First byte says that it is add immediate with 3 operands. Okay. So that means we need to look for further bytes. We look at next byte. It says that it is register mode. Okay, and register number is R1. So we are done with the first operand. Then, since there are 3 operands, we look at further bytes. Uh, this says that it is a base plus index, and register specified is R2, but we need to look at the offset, which is in the next 2 bytes. So look at byte 4 and 5, which specify the constant 737. For third operand, we go further down, look at byte number 6, which says that it is immediate, 4 byte immediate. So we look at 4 more bytes to get this constant 456. So it's a 10 byte instruction, but then you can get the idea of whole instruction uh, in several steps only. So just by looking at the first byte, you don't know how many bytes the instruction would occupy. Okay, as you come across mode fields, you get to know. So you can imagine that byte 2, for example, is specifying mode and a register. So 4 bits are going for register and 4 bits are specifying the mode, one of the 16 possible modes. In this case, the mode here was register mode. It was uh, register index mode. Here it was immediate mode. You can get the idea of orthogonality here. Okay, so you could have used uh, any mode for here for this. Of course, when it is destination, you can't have immediate mode, but other modes are possible. So the instruction itself does not restrict what mode you have for the second operand, what mode you have for the third operand, and accordingly, a certain number of bytes would be used to specify that operand. So all combinations which are meaningful are possible. Another example of back instruction. So this opcode is add 2 packed decimal numbers. Okay. Uh, so OP packed decimal number means that it is a sequence of decimal digits, each encoded in 4 bits. Right? So OP1 and OP2 specify length and the starting address of number 1. OP3 and OP4 specify length and the starting address of number 2. And OP5 and OP6 specify length and starting address of sum. So it's a total of 7 byte instruction. 1 byte will give the opcode and remaining 6 bytes specify this. Any question here? Okay, so finally let's talk a little bit about Intel's x86. So it has a long history in the sense that Intel started with a 4-bit processor, which was essentially a toy used for very simple embedded applications. Then came up with 8-bit, 16-bit, 32-bit, and 64-bit. So starting the journey from 1978, 4 and 8-bit architecture were even before that, early 70s. And in 78, the first 16-bit architecture. And this did not have floating point operations, which was provided as a co-processor, as a companion chip. You have 8086 chip. If you want to build system with floating point, you put this as additional chip. So this is not showing everything in the sequence of generation. There is 80186 also. 8286 is 24 bits address space. But the data is still, I think, 16-bit. 386 is 32-bit fully, both address space and address and data. Then in 89, Pentium was introduced. So initially there was, 89, 8486 was introduced, and I think a couple of years later, Pentium Pro with the performance enhancements. Then Pentium with MMX, which stands for multimedia extension. Okay. So to help in processing pictures and videos and audio. So there is a series: Pentium, Pentium 2, Pentium 3. Pentium 3 had streaming SIMD extension, or SSE. SIMD I mentioned as single instruction multiple data. So it allows one instruction to operate on multiple elements of data. So what is noticeable here is that there are several generations, and there has been an attempt to maintain compatibility. So you add features, you don't subtract anything, and keep on adding and bringing out new generations. In between, you see another company, AMD, implementing the same instruction set which Intel had designed. So the instruction set is fairly huge, almost 900 instructions, and these also are of variable size, 1 byte to 17 byte long. Uh, but it doesn't have 3 address instruction. So one operand must act as both a source and a destination. And one operand can come from memory, not both. So there are fairly complex addressing modes. You could have base plus scaled index with variation in displacement. You can have 8-bit displacement, 16-bit, or 32-bit displacement. But all addressing modes are not applicable to all instructions. So the combination of instructions and addressing modes are very irregular. There are lots of special cases which are hard to remember and learn. The effect of each instruction on condition codes is also very complex and irregular. So irregularity means that you have lots of special cases. Some are restrictions, and there's no uniformity. So as the processor generations have grown from 8 to 16 to 32 to 64 bits, the register structure has evolved, but basically taking same register and making them larger. So for example, in 8-bit, look at the bottom row, 8 for 8-bit processor, there were registers called AHAL. These are 8-bit registers. Okay, the horizontal dimension I have tried to keep uh, uh, commensurate with the uh, word size. Okay, so here you have 8-bit registers. They're called AHAL, CHCL. H and L stand for higher part and lower part. Okay, so you could treat this combination of registers, this pair of registers, as one 32-bit, sorry, one 16-bit register, or two halves, lower and upper half, 8-bit registers. So you could use AL, AH separately or combination as 16-bit registers. Similarly, C, D, and B. Then as design moved to 16 bits, uh, these registers became AX, CX, DX, and BX. X for extended. And additional register came up: stack pointer, base pointer, source index, destination index. Uh, in 32-bit, AX becomes EAX, CX becomes ECX, and so on. SP becomes ESP, and so on. So you can see that uh, there is no concept of general purpose registers, R0, R1, R2, R3. So you could just refer to them by their index number, their address. Here, there is specific role for various registers. Each register seems to have a different name. Okay. There are 16-bit segment registers apart from what I had shown. So this doesn't show the segment register. There are additional segment registers, which means each segment register specifies a segment of the memory, and then addresses are within that segment. So CS is code segment, stack segment, data segment, uh, and these are some additional segments. A peculiar feature of 86 instruction is that you can have prefixes for the instruction. That means before the instruction, you put some additional information which which specifies something about the instruction. So, for example, the prefixes could be used to override the default data size. So, an instruction may have default data size, let us say 16 bits, but prefix could be used to change that default size. So, override default segment register, uh, override default address size, or repeat the instruction. So, uh, you may have instruction which you want to repeat, say 10 times. A prefix could be used to specify that repetition. And lock bus, for example, let's leave that for the moment. I think it will be difficult to appreciate that. This shows some format. Uh, there are 0 to 3 bytes of prefixes, 1 to 3 bytes of opcode, mode or register memory specification, 0 or 1 byte for that. SIB stands for scale, index, and base. So 0 or 1 byte for that, up to 4 bytes of displacement, up to 4 bytes immediate constant. So if you add the max of these, you have 4 plus 4, 8, 9, 10, 10 and 3, 13 and 3, 16. You can see that this arrangement could go up to 16 bytes. And the least would be, if you take the minimum one, could be a single byte of code. Others could be all zeros. So mode specification, addressing mode, your 2 bits, 3 bits specify register, and these 3 bits specify register or memory. Scale, index, and base. So this is another 8-bit field. Here are some examples of instruction formats. You could see the variation. This is just 1 byte, push ESI. This is 2 bytes. This is jump if equal. Okay, and there is a displacement. The call, which is 4 and 1, 5 bytes. Move instruction, 3 bytes. Okay, add instruction with one of the operand is immediate. Uh, this is 4 bytes plus 1, 5 bytes, and so on. So you could see that there is such a large variation in the instruction size, and variety of formats are there. Here is a link to the listing of x86 instruction, and you would see that it runs in 2 pages. Okay, that's all for the moment. Thank you. If there are any questions, I'll try to address those.
Excuse me, sir.
Yeah.
Sir, how are we supposed to remember all this? Like, there are so many instructions of different type. Hello, am I audible? Excuse me, sir.
Yeah.
Sir, how are we supposed to remember all this?
Oh, you don't have
I
to
mean,
remember this. I think you
oh,
just get the basic idea. So none of uh, these factual things you don't have to remember. You can always
oh,
make references to these.
okay. So
Hello.
will we be doing projects on these also, like different kind of instruction
Uh,
sets also?
no, I think that is something which cannot fit into one course.
Oh,
So
okay.
as far as courses is concerned, the lab part will be confining to ARM processor. After this programming exercise, we'll start with the design exercise.
Okay, sir. Thank you.
Hello, sir.
Yeah.
Sir, our smartphone devices are based on ARM and the Windows laptop are based on x86, right? Like mostly, I'm not
Largely,
saying
yes. Yeah. Largely